Good afternoon. I'm Chuck Hornaday with Vados Remediation Technologies, here to present stabilization of PFAS and metals impacted soil. Before I begin, though, I would like to make a couple of housekeeping comments. First, you've been logged in as a participant in a listen-only mode. If you do have questions that you'd like to ask, you can enter them in the chat box, and those questions will be addressed after the presentation. So without any further ado, I'll go ahead and get started. This is a sort of a fundamental presentation on stabilization of soil stabilization applications. So the beginning of the presentation sort of outlines, the basics, if you will. So what is solidification and stabilization? Solidification and stabilization is intended to protect human health and the environment by immobilizing contaminants within the treated material. This usually involves mixing amendments into the contaminated soil, sediment, or sludge. There's a wide range of amendments that are used in that application. But ultimately, their goal is to either make physical changes to that media or chemical changes to the media. And we'll explore that in a little more detail. First, a little history on solidification and stabilization. This technology has been around for quite a long time, having been used in the 1950s for stabilization of radioactive waste, later adopted in industrial waste management in the 1970s, and then in the 80s being used in more remediation applications at Superfund and other environmental remediation projects. What it looks like essentially is something like this, where soils contaminated are mixed with a large diameter auger mixer, mixing in these amendments to help to stabilize those soils. That auger is moved from location to location to ultimately result in a large solidified or stabilized mass of contaminated soil or media. It can be done in a number of different ways, typically mechanically mixed for in situ applications, which would involve chemical feeders ultimately feeding these amendments into the mixing head so that it would mix the amendments uniformly into the soil. And also solidification or chemical stabilization can be done in an ex situ applications, which may involve chemical feeding and other mixing equipment. Some of the basic principles of stabilization, essentially for organic contaminants, the primary objective is to enact physical changes to that media, essentially things like compressive strength or permeability. We want to affect those types of properties of the media to result in reduction and mobility of those contaminants. Secondarily, chemical changes might also be enacted into those contaminants, and that might include things like in situ geochemical stabilization or reducing the leachability of certain contaminants from the soil. For inorganic contaminants, typically the primary objective is chemical change. So it might mean adjusting the pH to reduce to reduce the leaching of those contaminants such as metals, and then secondarily the objective might be to solidify or stabilize chemically solidify in place the contaminants. The chart on the right is just an illustration of the amphoteric nature of various metals. You can see that within a certain range, for example, for lead between 9 and 10 pH, it has the lowest solubility. And so that we know that by controlling pH, we can stabilize that material and reduce its leachability. Some of the typical tests that are done in the feasibility and mixed design process include, for physical testing, include hydraulic conductivity. That's that picture in the middle where you see triaxial permeameters measuring the rate of flux of water through that solidified sample. Also, we test unconfined compressive strength. Other tests that might be conducted include freeze-thaw durability or wet-dry durability, free liquid tests such as the paint filter test, moisture content, and density. Essentially, the purpose for changing the permeability or reducing the permeability is to reduce groundwater contact with that solidified mass. So as you can imagine in the illustration shows that as groundwater were to essentially percolate through contaminated mass, you're going to be picking up contaminants as it flows through. And by reducing the permeability, you're able to redirect that flow around the solidified soil mass and reducing the mobility of those contaminants. Some typical properties in terms of physical performance properties that are evaluated. I mentioned unconfined compressive strength. Often the design might call for a compressive strength of 50 psi. It is very much site specific and not always a requirement depending upon how the site will be used ultimately. And hydraulic conductivity, permeability of 1 times 10 to the minus 7 centimeters per second is a typical goal for solidified soil that has organic contaminants. And then finally, leachability, or the ability of these contaminants to migrate out of that mass. An example of that is the TCLP test for metals. If you have more than 5 milligrams per liter of leachable lead, for example, that's a performance criteria that shows that that soil would be considered to be hazardous waste. Now, further to leaching testing for chemical analysis of these, the effectiveness of these different solidification or stabilization methods, I've mentioned the TCLP. Essentially, that is determine the toxic characteristic leaching procedure is intended to evaluate whether the waste is considered toxic or hazardous or non-hazardous, depending upon that criterion. This involves using organic waste and essentially percolating it through crushed monolith. So it's intended to be a 100-year simulation of materials that had been co-disposed with organics in a municipal solid waste landfill. The next test is the synthetic precipitation leaching procedure, or SPLP test, method 1312. This test uses an inorganic acid with a pH of 4.2, also on the crushed monolith. Now this also, that pH can be adjusted to be more representative of precipitation in a particular part of the country. This test too is intended to be a 100-year simulation to simulate the leaching from repetitive exposure to acid rain. So as you could imagine, this might be more appropriate test to run if you're simulating materials that had been stabilized and left in place, rather than something that was we're trying to determine if it is characteristically hazardous or not. So an SPLP test might be chosen instead. Another test for evaluating chemical durability or leaching is the multiple extraction procedure, or MEP, method 1320. This is a long-term stability test. It involves essentially that TCLP test followed by an additional 9 sequential extractions, with the intention there being to simulate leaching from repetitive exposure to this acidic leachate over a 1,000-year period. So certainly a long-term, a very good demonstration of long-term durability. Other methods more recently developed include the leaf methods. There's 4 of those, all of which are considered the semi-dynamic leaching procedures, methods 1313 through 1316, and each one is uniquely designed to evaluate certain aspects of the leachability, if you will, of these contaminants. 1313 measures the leaching in a batch extraction procedure and correlates that with the effect of the pH. So you can see how change in pH will affect change in leaching. Method 1314 is similar in nature, however, it's done in a column test. Method 1315 is used to measure the rate of mass transfer from the monolith in a tank leaching experiment. So again, in this case, you're measuring how much the rate at which contaminants are migrating from this monolith. And then finally, method 1316 is measuring leaching in a batch extraction method as it's affected by the liquid solid ratio. So essentially, depending upon how much liquid there is in relationship to the solid, how does that affect leaching of these contaminants? A little bit more about the leaf method. This specifically the 1315 method, as I mentioned, it's been developed to determine the mass transfer of release rates of the COCs from a low permeability material under diffusion controlled release conditions. So as I said, it's one of 4 different leaf methods which were developed as a collaboration between the US EPA and a number of other research organizations. Just an illustration of that, essentially, as we've described, you're taking multiple extractions from the solidified mass, depending upon what you're evaluating for, X number or N number of intervals, and essentially using that data to determine the performance of the solidification and stabilization. So what are these agents that are used for solidification and stabilization? There's a wide range of them. We're going to discuss the ones that are highlighted here: Portland cement, and then these others: cement, kiln dust, slag, fly ash. Those are all pozzolanic in nature, often added in conjunction with Portland cement, and then some other proprietary media as well. Portland cement is a generic material. It's been produced by a number of companies all over the US, all over the world. Obviously, the cement is used. It's the same cement that's used in the creation of concrete, which contains Portland cement and aggregates as well as water. In this case, we're using the cement in a solidification and stabilization application. It's been used for a long period in time. Portland cement is very commonly used to immobilize the contaminants. As we know, it sets up and creates a high compressive strength, and when it's stabilized in a solidified mass monolith, it is low in permeability as well. These materials are manufactured to standards created by the ASTM and the Portland Cement Association, ACI, American Concrete Institute. And so therefore you can expect very uniform, very high uniformity there. They're readily available, and there's not necessarily true that Portland cement is the magic bullet that fits all solidification and stabilization applications. We're going to talk about stabilization of PFAS compounds, and we're going to see the effect that Portland cement has on that. So it's some interesting data which I'm going to be sharing with you here later in the presentation. The next amendment that's used in solidification and stabilization is sodium bentonite. This is a high swelling clay that's composed of the mineral sodium montmorillonite. It's often used or sometimes used as an additive to Portland cement mix designs to further reduce the hydraulic conductivity. It too is produced to specifications consistent with the API, American Petroleum Institute. It's available from various manufacturers around the country in a wide range of particle sizes for various applications. Typically in an in situ stabilization application, you would use a powdered size grain and then mix it into a slurry. One thing also to note about bentonite is that it is intended for use in freshwater applications it's important to know that sodium bentonite doesn't hydrate and turn into a slurry nearly as well in the presence of salt water as it would in fresh water. The next amendment that we'll talk about is organoclay. This is a sodium bentonite that's actually been treated and converted from being hydrophilic to organophilic. So it no longer wants to soak up water. In fact, it will repel water, and it works as a filtration media. This material is used in filtration applications to remove organic contaminants, especially separate phase organic contaminants from waste streams. So again, it's got a high affinity for these organic contaminants. And so therefore, when it's used as an additive with Portland cement, it will reduce the leaching of those organic contaminants from a stabilized or solidified mass. This material should be, the manufacturers are able to provide quality control documentation on it. There is very good data showing its ability to reduce leaching of non-aqueous phase liquids at relatively low addition rates, say 2 to 4%, and it is available in a powdered form. One other comment about that, there are in fact models for predicting leachability of these organic contaminants from solidified mass when Portland cement and organoclay are used together. A variety of different US EPA guidance documents have been written, which include discussion on the use of organophilic clay and in solidification stabilization applications. Rather than read all this information, just to suffice it to know that these documents are out there, that you can read more about the use of organoclay in ISS applications. The next technology I'm going to talk about is Blastox. This is a fine-grained calcium silicate material. It is designed to reduce leaching of metals from soils and can be used in either an in situ or ex situ stabilization application. The idea initially is to ensure that the materials will pass a TCLP test and will render them as non-hazardous waste. But later, more recently, Blastox has been used in situ stabilization applications for stabilizing those metals in situ and prevent and reducing leaching of those metals. There are a variety of different formulations of Blastox that are effective on a range of metals, from chromium, cadmium, lead, arsenic, and these again are also, there's good data that shows that by adding this calcium silicate to these metals, it can reduce the bioavailability essentially of these metals as well. So we can reduce leaching and bioavailability. These materials are available in a range of particle sizes and are also effectively absorb free water. Just to illustrate the particle sizes from a powder to a fine grain to coarse grain, depending upon the application. In most in situ applications, we would use a powder or Bantox type material. For ex situ stabilization, most commonly the Blastox 215 is the choice. How does it work? It actually has 3 different mechanisms by which Blastox works. First, it does release alkali to adjust the pH. As we've talked about, hitting a pH range between 9 and 10 is ideal for reducing and slowing the metal dissolution. So putting that soil in the proper range will help to reduce leaching. It also chemically converts through an addition and substitution reaction, essentially complexing with the lead to form a less soluble form of it, and that would be, for example, a lead silicate. And finally, it does work through a micro and macro encapsulation process where the soils essentially crust up and become lower in permeability. And as we've discussed, reducing the flow of water through the waste will result in less contact with the contaminants and less leaching of the contaminants. Finally, so the point being, there's multiple mechanisms there that are effective at improving the performance of Blastox and reducing the liability related with metals. Some additional testing has been done to demonstrate long-term stability of blast ox. We've talked about TCLP for characterizing the waste, the MEP method for long-term stability. This method uses a pH of acid with a pH of 3 versus 4.88 for a typical TCLP test. And as I described, it's an additional 9 sequential cycles of extractions. This test is designed to eliminate the buffering capacity that comes with a pH adjustment, so that it demonstrates that the pH adjustment isn't the sole safeguard protecting or preventing leaching. Some chemistries, such as calcium oxide or magnesium oxide, have performed poorly as they are strictly a buffering agent and simply adjust the pH. And once that pH buffering capacity has been exhausted, then the leaching will begin. However, several federal agencies have tested blast ox chemistries in various different ways. The US EPA, the Federal Highway Administration, and the Department of Defense have all tested the technology and concluded that they're very stable and durable, even when tested using the MEP for long-term durability. The method of installation for ex situ applications, or method of application, is simply to consolidate the surface soils and then apply the blast ox at the appropriate dosage rate. Treatability studies are conducted in order to verify the appropriate dosage rate to ensure that leaching will be below the maximum allowable. And then the materials are mixed together using a mixing head on the end of an excavator to ensure uniformity. If a backhoe were to be used, 5 or 6 turning it over with a backhoe would be suitable enough to create those mixing. But there is no waiting for samples to cure. Essentially, as soon as the materials are mixed together, they can be sampled, taken to the lab, and tested. The materials available in bulk bags and also by bulk delivery in pneumatic trucks. Again, it's mixed thoroughly with the soil, no residence time required. And after mixing, then the samples are collected and sent to the lab. Now, other methods of mixing could also be used, such as a pug mill or some form of continuous feed process. For in situ applications specifically, you might apply the blast ox to the top of the soil or lift that you're planning to treat, and then mix that material in place, again, with an excavator, turning it over 5 or 6 times. Other equipment that could be used for that application is something like a hollow stem rotary auger or similar equipment, such as shown in the middle illustration there. The ALU equipment has a separate tank for the amendment, which is pneumatically blown down the stem or the stem of the mixing head and then introduced to the soil as it's mixing. Some additional laboratory test data. This is some data that was presented at the Battelle Chlorinated Conference in 2018 by Robert Thomas of GHD. And in this case, they were doing some treatability studies to stabilize lead at a former oil refinery. They took 150 grams of soil and mixed it with various reagents, placed them in molds, and allowed them to cure for 21 days. Not necessary if it were strictly blast ox. However, that most of these samples included the use of cement as well. Then they conducted TCLP tests to determine leachability and evaluated which were the most effective amendments. On the top chart, you can see the initial characterization. Basically, they broke it down into sort of 3 ranges of lead concentrations. The lower level being those with total lead of 8,600 approximately milligrams per kilogram. The middle level being around 20,000 milligrams kilogram, and then the high level being about 41,000 milligrams per kilogram. In all cases, you can see that the leachable lead was well in excess of that characteristic criteria of 5 milligrams per liter. The various different amendments were added. The control sample, curiously, those numbers were all significantly lower than those in the initial characterization. However, at 10% addition, then we had a mixture of 5% cement and 10% fly ash, and then finally a mixture of 5% cement and 5% blastox. Interestingly, that the 10% addition at the low lead concentration sample exceeded the allowable 5 milligrams per liter. When fly ash and cement were mixed, none of the samples were able to achieve the leachability requirement of 5 milligrams per liter. And then in the case of the blastox, all of the samples were well below the required threshold. What's interesting about this test is they did not test blastox alone. However, I'm certain that the results would have been as good as what we see in the blastox and cement. However, one thing to note is that in this case they had a compressive strength requirement, and so they did add cement along with the blastox. Just some final thoughts about in situ stabilization of various materials, specifically metals. So these treated soils, we have been using blastox for stabilization of chemicals, of leachability of metals for a long time, and characteristically non-hazardous, rendering them as characteristically non-hazardous. However, more recently, we've seen an interest in situ applications. Certainly, the market is changing, and the economics of being able to treat soils and leave them in place is beneficial to remediation. So it really is very much, though, dependent upon state and local requirements for whether that would be allowable. I happen to be in Illinois. They seem to be fairly favorable to this option of treating soils, metals, contaminated soils for in situ stabilization. It's mentioned it can be mixed with cement to improve the compressive strength, but not necessarily required. Testing methods for the metals leachability should be evaluated. So what we're saying here is a standard TCLP test is good to characterize soils, but is it appropriate? Should SPLP or MEP or one of the leaf methods instead be considered if you're looking at using in situ stabilization technologies for and leaving those soils in place? You want to do a test that's going to be most representative of what how those soils will be affected in the longer term. You can also evaluate treated soils for bioavailability using method 1314, a standard operating procedure for in vitro bioaccessibility assay. So this is a way to demonstrate that stabilizing these soils will reduce bioavailability of the metals. And then finally, as just related to that, the EPA has some data that has indicated that certain forms of lead, such as lead silicates, are in fact less well absorbed than other forms. So it's good to know that complexing the lead with an agent such as calcium silicate can reduce uptake of these contaminants. Finally, I'm going to move on to a discussion about Fluoro Zorb. This is a surface modified clay. It's designed specifically for filtration applications and in situ stabilization applications of perfluorinated alkyl substances, or PFAS compounds. I would imagine by now most everybody has heard about the forever chemicals we refer to as PFAS, or a very wide range group of chemicals. These chemicals are bioaccumulative and persistent and don't break down very readily. And so they're kind of the latest class of environmental concerns. Fluoro Zorb is a media that's been designed specifically to remove them from in flow-through filtration applications, and as well as to stabilize them in contaminated soil. So as similar to what we've been talking about, this will reduce the leaching of them from the treated soils and prevent them from migrating further, through the groundwater or in other ways. One thing that's unique about this Fluoro Zorb technology is that it's not susceptible to competitive sorption or impacts from co-contaminants. Other filtration media, such as granular activated carbon, is much more affected by co-contaminants that might take up sorption sites or in fact kick off contaminants that have all previously been sorbed. Data has shown, which I'm going to present, that by adding Fluoro Zorb at very low rates can reduce the leaching of PFAS significantly to below the current health advisory levels. And this material too is available in a powdered form for in situ stabilization applications. This chart basically gives a range of the different products that are available. However, as we've mentioned, the first column here, Fluoro Zorb 100, is the one that would be typically used in situ stabilization applications. So going on to some work that has been done on Fluoro Zorb, this first study was by Peter Storch of Arcadis in Australia, presented at the proceedings of a cleanup conference in Melbourne, Australia in 2017. And essentially what we have here is some leaching testing that was done first on the control sample, had a 228 milligram per liter leaching of PFAS, total PFAS compounds. The second control, when stabilized with cement, that number was reduced to 1.17 milligrams per liter. A proprietary blend of aluminum hydroxide and carbon was added as an alternative and was able to reduce the leaching to 0.75. But interestingly, when that was blended with cement, in fact, the leachable PFAS was higher than the control sample. It's an interesting phenomenon we'll see again, and we'll talk about what that might be. We think this to be either an effect of pH or possibly the heat of hydration causing some volatilization of these PFAS compounds. When Fluoro Zorb was added, the total PFAS was able to be reduced to 0.3 milligrams per liter, and Fluoro Zorb and cement had the best performance at 0.04 milligrams per liter. So this work was done more recently. The same bench testing was repeated by Arcadis, and then Fluoro Zorb was selected for a field pilot. It was installed in 2018 with 5% Fluoro Zorb and 10% Portland cement as the mix design, and then annual SPLP sampling and SPLP testing will be conducted to verify long-term performance. However, that it takes time for that data to become available, and so far it's not. We did some go to a university and have some additional testing done to verify the performance of the Fluoro Zorb media. This slide here is just some characterization of the soil that was used at University of Texas to do these leach testing of Fluoro Zorb in this particular soil. So as you can see, the total leachable PFAS in the soil was approximately 40,000 parts per trillion. Various different PFAS compounds in the soil. I think there's 32 listed there, many of which were above that 70 parts per trillion health advisory level. This slide kind of illustrates the results in a nutshell, if you will. That orange dot on the top left there represents the total soil only leachable PFAS, 32 of the 32 PFAS compounds, approximately 40 parts per trillion. Looking at the curves, this gray curve at the top, you see This is 0% Fluoro Zorb, so essentially just the Portland cement. The x-axis represents the addition of Portland cement, the addition rate. So you can see Portland cement was effective initially, reducing it, the leachability of the PFAS, but then you see this tailing upward effect. And we believe, again, that this is a result of either pH or possibly heat of hydration. When we blended Fluoro Zorb in at as low as 1%, Fluoro Zorb 100 with these various different rates portions of Portland cement, you can see that we were getting significant improvement in the leachability of these PFAS compounds. And at one formulation, 5% Portland cement, we were able to be below the health advisory level of 70 parts per trillion. But again, we see that effect where it tails upward again when there's an increase in Portland cement. And then finally, the blue line represents a 5% Fluoro Zorb addition, and you can see in all cases that we were able to achieve results below the health advisory limit of 70 parts per trillion. So that was a pretty positive demonstration that Fluoro Zorb would effectively reduce the leachability of these PFAS compounds from that soil. Now, some of the conclusions from the University of Texas study were that really all of the PFAS were reduced to low concentrations for all of the mixed designs that contain the Fluoro Zorb 100, regardless of the ordinary Portland cement content. So point being that this wide range of 32 different contaminants were all effectively reduced. Ordinary Portland cement alone was not effective in stabilizing these same constituents. So this is an important point that I made at the beginning of the presentation, that you cannot expect to use cement in an ISS application for PFAS compounds and that it will have a positive effect on reducing leachability. And next is that some of the constituents specifically were detected at even higher levels than in the soil alone. This is that point that Portland cement, in fact, increases the mobility, or appears to increase the mobility of these certain compounds. And finally, a mixed design of 5% Portland and 5% Fluoro Zorb gave the optimal performance when tested using method 1313 and 1315. So with that, I've kind of given you guys a summary overview of solidification and stabilization applications, including the history, typical application methods, test methods for physical and chemical properties. We've provided an overview of various different amendments that are used commonly in solidification and stabilization applications for organic and inorganic compounds. And we've introduced a few new amendments that have shown good promise in stabilizing metals, as well as these new class of compounds, PFAS. So with that, I would like to say thank you for participating in today's webinar. If you have questions, they'll be addressed as a follow-up to the call. Thank you.